1.6, relative motion. An airplane flight is an excellent example of relative motion. The view from an airplane window provides a different perspective than the view from the ground. When analyzing relative motion, we use the vector symbol v with an arrowhead on top, with two subscripts in capital letters. The first capital letter represents the moving object. The second capital letter represents the frame of reference.
Tommy Acchetti, report to the attendance office. Tommy Acchetti to attendance.
Let's jump right in to sample problem number 1 and see this notation at work. For example, suppose an airplane, symbol P, is traveling at 450 kilometers per hour north relative to the air. And the velocity of the air, A, relative to the Earth, E, is 40 kilometers per hour. What is the velocity of the airplane relative to the Earth as seen by the observer? So what they are asking us to find is the velocity of the airplane relative to the Earth. The moving object is the airplane, and the frame of reference they are asking for is the Earth. So let's look at what's given in this question. We know the velocity of the plane is 450 kilometers per hour. And this is the velocity of the plane relative to the air. So I write velocity of plane relative to the air is 450 kilometers per hour north. I also know that the velocity of the air relative to the Earth, velocity of air relative to the Earth is 40 kilometers per hour north. So what I want to find is the velocity of the plane, and I'm going to use the letter P for plane so it doesn't get mixed up with air. The velocity of the plane relative to the Earth. Now I want you to see this for a moment. This is what I want to find, the velocity of the plane relative to the Earth. I am going to spread these apart. I know the velocity of the plane relative to the air. I know the velocity of the air relative to the Earth. So if I add these two together, I can find the velocity of the plane relative to the Earth. So this is what we're going to do, literally. This is our equation. We know the velocity of the plane relative to the Earth is 450 kilometers per hour north, plus the velocity of the air. So, sorry, the first one was the velocity of the plane relative to the air is 450 kilometers per hour north. And the velocity of the air relative to the Earth is 40 kilometers per hour north. These are collinear, same direction vectors. So we can add them together. We get 490 kilometers per hour north. So the velocity of the plane relative to the Earth is 490 kilometers per hour north. If you were observing the plane from the Earth, that's the speed it would appear to you. Let's look at sample problem number 2. Passengers on a cruise ship are playing shuffleboard. The shuffleboard disk's velocity relative to the ship is 4.2 meters per second forward, and the ship is traveling in the same direction as the disk at 4.6 kilometers per hour relative to the Earth. And this is when the water is stationary. A few things that I want to write. The disk, we're going to give the symbol D. S is going to be ship. E is going to be Earth. The other thing I want to do is convert 4.6 kilometers per hour into meters per second. So I want to get rid of the kilometers, and in the place of kilometers, I want meters. In order to get rid of the kilometers, I would need kilometers on the bottom so that I can cancel them out. I can't cancel them out until I state the relationship between the meter and the kilometer. And that relationship is there are 1,000 meters in 1 kilometer. Next, I want to get rid of the hours on the bottom, and I want seconds. In order for the hours to cancel out, I would need hours on top. If I have one on top and one on the bottom, they'll cancel out. In order to do so, I need to state the relationship between the hour and the second. And I know 1 hour has 3,600 seconds. Multiply everything along the top, divide by everything along the bottom, report your answer to the same number of significant digits as there are in the original measurement. The numbers 1, 1,000, and 3,600 do not affect the accuracy of this. These are accepted values. They have infinite significant digits. If we punch it into our calculator, we end up with 1.3 meters per second forward. So let's list everything we have. We have the velocity of the disk relative to the ship, and it is 4.2 meters per second forward. We also have the velocity of the ship relative to the Earth, and we just converted it. It's 1.3 meters per second forward. I want to find the velocity of the disk relative to the Earth. So I have ds and I have se. If I overlap these two, I will be left with the velocity of the disk relative to the Earth. Bring them together, bring these velocities together such that when you add their subscripts, the first subscript and the last subscript are the ones that you want. So I am going to add up the velocity of the disk relative to the ship plus the velocity of the ship relative to the Earth. My starting variable is d. My last variable is e. My answer will therefore be d e. And that's 4.2 meters per second forward plus 1.3 meters per second forward. Therefore, the velocity of the disk relative to the Earth, if we add these two numbers, they are collinear, they are same direction, we end up with 5.5 meters per second forward. Part B, determine the velocity of the disk relative to the Earth when the disk is moving in a direction opposite to that of the ship. So the velocity of the disk relative to the ship is 4.2 meters per second backwards. And the velocity of the ship relative to the Earth is 1.3 meters per second forward. So I want the velocity of the disk relative to the Earth. So I'm going to combine these speeds such that their symbols, their variables, the first is d and the last is e. And that works if I do the velocity of the disk relative to the ship plus the velocity of the ship relative to the Earth. .2 meters per second backwards plus 1.3 meters per second forward. These are collinear, but they are not in the same direction. So we are going to write this as 4.2 meters per second backwards minus 1.3 meters per second backwards. Change the direction, change the sign. If we simplify this, 4.2 rather, minus 1.3, we get 2.9 meters per second backwards. Therefore, the velocity of the disk relative to the Earth is 2.9 meters per second backwards. In part C, we're going to throw in an extra frame of reference. Now the water is moving as well. So we know the velocity of the disk relative to the ship is 4.2 meters per second forward. We know that the ship is moving 1.3 meters per second. But now this is relative to the water, not relative to the earth, relative to the water. Before, the water wasn't moving. And I know the velocity of the water relative to the earth is 1.1 meters per second forward. So what I want to find is the velocity of the disk relative to the earth. My first variable has to be d, and my last variable has to be e. I need to pair these three up, overlap variables where I can, so that I start off with d and I end up with e. If I'm starting off with d, I need the velocity of the disk relative to the ship. Now, the next variable that I put in needs to start with an s in order for me to combine them. So I am going to use the velocity of the ship relative to the water. My next variable has to start with a w if I want to pair them up. So I'm going to do velocity of water relative to the earth. When I combine these together, my starting variable was d. My ending variable, my end variable, was e. When I combine them together, I'll get the variables d, e. So let's add these up. We have 4.2 meters per second forward plus 1.3 meters per second forward plus 1.1 meters per second forward. Punch this into our calculator, and we get 6.6 meters per second forward. Let's take a look at sample problem number 3. We have a boat that is trying to cross the river. So it is going to head north across the wide river. But the river has a current. So as this boat travels north, the current is traveling east. The boat is going to travel north, and the current is going to travel east. As a result, as this boat tries to cross, as it tries to move forward, as it's moving forward, the current is going to push it east. And it will have a resultant velocity. And the resultant velocity can be found by adding the velocity of the boat relative to the water and the velocity of the water relative to the earth. When you add those together, when you add the velocity of the boat relative to the water, 10 kilometers per hour north, plus the velocity of the water relative to the earth is 5 kilometers per hour east. If we add this vector plus this vector, we can use Pythagorean theorem to find the resultant. What they want us to find is the velocity of the boat relative to the earth. So our starting variable has to be b, and our end variable has to be e. So if we do velocity of boat relative to water plus velocity of water relative to the earth, we will start with b, we will end with e, and our w's link them together. They are the same. We can combine them. So let's add them using trig. We have 10 and 5. So the velocity of the boat relative to the earth is the square root of 10 squared plus 5 squared. If we punch this into our calculator, we end up with 11.2 kilometers per hour. Now we need the angle. We're going to use opposite and adjacent and the trigonometric ratio inverse tan, which is 5 over 10. So the angle, if we punch this into our calculator, we get 27 degrees. So the velocity of the boat relative to the earth is 11.2 kilometers per hour, 27 degrees east of north. The boat will point north. The water is flowing east. The resultant velocity will be 27 degrees east of north. Now these were all collinear or perpendicular, and they were easy to solve either using algebra or trig. What if we have non-collinear, non-perpendicular vectors? Let's try sample problem number 4. The air velocity of a small plane is 230 kilometers per hour, 35 degrees east of north, when the wind is blowing at 7.75 kilometers per hour, 25 degrees south of west. Determine the velocity of the plane relative to the ground. So we have the velocity of the plane relative to the air is 230 kilometers per hour, 35 degrees east of north. And we have the velocity of the air relative to the earth is 75 kilometers per hour, 25 degrees south of west. I'm going to draw a rough sketch of what these look like. Let's break each of these vectors up into x and y components. The velocity of the plane relative to air in the x direction is going to be 230 cos 35 degrees. 230 sine 35 degrees. This is the opposite with respect to the hypotenuse and the angle. If we punch this in, we end up with 130 kilometers per hour east. The velocity of the plane relative to the air in the y direction is going to be 230 cos 35 degrees. If we punch this in, we end up with 190 kilometers per hour north. We'll do the same for the velocity of the air relative to the Earth in the x direction and the velocity of the air relative to the Earth in the y direction. In the x direction, the x component is the adjacent with respect to the hypotenuse, so we get 75 cos 25 degrees. If we punch this in, that is 68 kilometers per hour west. Whereas the y component of the velocity of the air relative to the Earth is the opposite with respect to the angle. So it's 75 sine 25 degrees. If we punch this in, we end up with 32 kilometers per hour south. So I need to find the velocity of the plane relative to the Earth in the y direction, which is equal to VPA y plus VAE y. We're starting with a P and we're ending with an E. What links these together is the letter A. So that means we can combine them. So we end up with 190 kilometers per hour north plus 32 kilometers per hour south. If we add this up, remember, one is north and one is south, so we end up with 190 kilometers per hour north minus 32 kilometers per hour south, or north rather. Change the sign, change the direction. We end up with 158 kilometers per hour north. Let's find the velocity of the plane relative to the Earth in the x direction by adding up. The velocity of the plane relative to the air, x, plus the velocity of the air relative to the Earth, x, which is 130 kilometers per hour east plus 68 kilometers per hour west. These are in opposite directions. We can change the sign to flip the direction. This becomes 130 kilometers per hour east minus 68 kilometers per hour east. And we end up with 62 kilometers per hour east. So we have the x component of the resultant velocity and the y component and we want to find the resultant velocity, the velocity of the plane relative to the Earth. We can use Pythagorean theorem to solve for the velocity of the plane relative to the Earth, as it is the hypotenuse of this right-angled triangle. Every time we use component vectors, we find the x components of each of the vectors, the y components of each of the vectors. We add up all the x components, add up all the y components, then we make a right-angled triangle like we have now. And our answer is always the hypotenuse, which we find as the square root of 62 squared plus 158 squared. If we find the answer with our calculator, we end up with 170 kilometers per hour. That's the magnitude of the velocity of the plane relative to the Earth. It's just the magnitude. If I want to find the angle, I need to calculate theta. I'm going to calculate theta, and every time we've done a right-angled triangle, finding the sum using vector components, we've always used the inverse tan of opposite over adjacent. So the angle is 21 degrees. I can now write the complete vector, the velocity of the plane relative to the Earth, is 170 kilometers, 21 degrees east of north. Try the homework questions provided.